Right, so welcome everyone. Now, second part of midterm 2018 review. Now, last thing we did was question 11 and 12. So you have these in the recording. So we're starting from question 13. Now, question 13 says, velvet worms use a cruel method of hunting. Aiming at their prey for distances of up to 1 meter, they eject two jets of a sticky liquid from glands near their mouth. The liquid dries very fast, immobilizing the prey. Okay. Now, the worm then injects digestive juices that cause internal liquefaction of the prey. Assume that the velvet worm's body has a mass of 17 grams and that it ejects 0.2 grams of liquid over a period of 0.35 seconds at an average speed of 5 meters per second. What is the average force the velvet worm needs to hold itself steady while ejecting the liquid? Now, it's a long question. So here we're looking for the average force the velvet worm needs to hold itself steady. Okay. Now, we're looking at the change in linear momentum, okay, over a certain period of time. So the starting point would be to use the formula for the impulse. So J, okay, is equal to the amount of force, okay, acting over a certain period of time, delta t, and this will correspond to the change in linear momentum, delta p. Now, of course, the force acting on the system, okay, will cause or will be caused by this change of linear momentum after ejecting this liquid, which means the velvet worm would move backward as a result of ejecting this liquid, okay? Now, to hold itself steady, okay, so we need to apply a force in opposite direction, which will be the same magnitude anyways, but opposite in direction. So in terms of magnitude then, to find the force, all you need is divide delta P, take the delta T here, downstairs under the delta P, and this is what we've done here, okay? So delta P over delta T, and of course, delta P is the mass multiplied by velocity final minus velocity initial, okay? Now, of course, initial velocity is 0, all right? For the liquid, okay, so what is ejected in this process is the liquid, okay? So it starts from 0 and final velocity is, we're saying is 5 meters per second, okay? Now the mass of this liquid is 0.2 grams, and it happens over a period of 0.35 seconds, okay? Now in this case, okay, so in this case, these are the numbers we're plugging into the formula. So 0.2, so we're talking here 0.2 grams. Of course, you need to multiply the grams into kilograms. So this is 0.2, that's why we're multiplying by 10 to the negative 3 here. We're not using grams. And then the velocity is already in meters per second, no need to convert. And the time is in seconds, so there's no conversion here. So all you need then is plug these into your calculator. You end up with this value for the force the velvet worm needs to apply to keep itself steady. Okay, so the answer then corresponds to option D. Now, question 14, concept question. You have an inelastic collision is one in which, now the correct answer, of course, is highlighted as momentum is conserved, but kinetic energy is not conserved, okay? Now, something we discussed in the lecture. So when you have inelastic collision, so when two objects collide, so let's say this is mass 1, moving with velocity v1 initial, and then we consider, if you remember, mass 2, v2 initial equals 0. So after collision, the two lock together and they move as one, v final. Now here they move as one, which means they have a total mass of m1 plus m2. Okay. Now in this case, the total linear momentum is conserved, which means m1 v1 initial will be equal to m1 plus m2 v final. Of course, in this case, m2 mass 2 doesn't have linear momentum because velocity initial for mass 2 is equal to 0. Okay, so the total momentum initially is this one, and the total linear momentum is this one. So this is conserved. But kinetic energy is not. Why? Because when they lock together, okay, some of the energy or some of the kinetic energy that was carried along by mass 1 will be lost in the process of sticking. So will be lost in internal internal stresses, internal let's say deformation as a result of sticking together or locking together. So part of the kinetic energy will be lost. It could be also lost in terms of heat, okay, which means kinetic energy is not conserved, but linear momentum will. Okay, right. So that's question 14, and we're rejecting the other options, which say, let's say option B, momentum is not conserved, but kinetic energy is conserved. That's not true. Momentum is conserved. The total impulse is equal to the change in kinetic energy. That is not true. So the total impulse is the force applied, okay, over a certain of time. It corresponds to a change in linear momentum, not change in kinetic energy. D says neither kinetic energy nor momentum is conserved. That's also not true. And last one is total mass is not conserved, but momentum is conserved. So that's not true because the mass is not going to be affected. So the mass will not vanish in the process of collision. Okay. Right, so that's question 14. Question 15. Now we had a similar, very similar question in the review on midterm 2019. So you have an 1100 kilogram car, mass 1, approaches an intersection traveling east, 25 meters per second. Okay, so in vector components, so you have 24 for the x component of velocity and 0 for the y component. And then you have a 1500 kilogram for mass 2 car approaches the same intersection traveling at 34 meters per second. So in vector components, that will be 0 for the x component and 34 for the y component. Now, the two cars collide at the intersection and lock together. See the figure below. Now, ignoring any external forces that act on the cars during the collision, what is the speed of the locked cars immediately after the collision? Now, again, we did this. We actually did this in the lecture. We did this in one of the review session actually on 2019. So the idea then is to use the conservation of linear momentum, okay, before collision. This is before collision. And we're putting mass 1 times velocity 1 as a vector initial, plus mass 2, this is mass 2, the 1500, okay, so 1100 is mass 1, plus mass 2 times velocity 2 initial. Okay, we have the components, and it's equal to total mass m1, sorry, m1 plus m2, m1 plus m2, that's the total mass, multiplied by v final, and this is our unknown, the final velocity. Right. So in this case, when you add, okay, so when you multiply, so there's different ways of doing it, of course. So here we multiply the 1100 times 24, the 1500 times 34, so we ended up with these numbers, okay, equal to total mass times v final. Now here, the v final will be then equal to, you add the two vectors, so these will be the vector components, and then you divide by the total mass, and this will give you the v final. Again, straightforward. Now, these are the vector components of final velocity. Vector components of vector velocity, which means if you need the magnitude of velocity, so this is the magnitude of velocity. Okay, so it's going to be root vx squared plus vy squared plus vy squared. All right, so we're using Pythagoras here, so the usual formula to calculate the magnitude of vector velocity, final velocity, and you get 22.1. Right, so this is then question 15. Question 16. Two meatballs are speeding directly toward each other. One is 4 kilograms, a 4 kilogram meatball moving with a speed of 6 meters per second, and the other has a mass of 2 kilograms and the speed of 4 meters per second. If they collide inelastically, now this is an inelastic collision, what will be the speed of the resulting 6 kilogram meatball immediately after the collision? So here, again, we're dealing with the following. So you have the mass 1, 4 kilogram, and mass 2, 2 kilogram. One is moving right, the other is moving left. And we want the velocity, what is the velocity of, 1 second. So we're looking for the velocity, the resulting 6 kilogram meatball. So when they collide, they lock together, the total mass will be 6 kilograms. So what would be the final velocity for the whole? Now, of course, conservation of linear momentum will be mass 1 times velocity 1. So that's 4 kilograms times 6 meters per second to the right, and then plus 2 kilograms times negative 4. So we need to take the second velocity for mass 2, because it's moving left. Okay, it is important to take the proper direction for vector velocities. So whatever moves right will be taken as positive, whatever moves left will be taken as negative. Okay, so here the negative 4 means the object is moving left. And it's equal to total mass m1 plus m2 times v final. That's what we have. We're just calling it v here for short, okay, instead of v final. So in the end, you have all the known values on the left side. So you end up with 24 minus 8 equals to 6v. And 16 equal to 6v, which means velocity, final velocity is 16 over 6, roughly 2.7 meters per second. And it's to the right. Why to the right? Because it's positive. If we found a negative value, that would mean we're dealing with an object or a velocity that is pointing to the left, okay, pointing to the left, right. Here in this case, it will be positive, so it's pointing right. Now, question 17, we have a bar of length L equal 4.4 meters is pivoted at one end, point P, and a force F equal to 12 Newton is applied at the other end, as shown in the figure. Now, if the angle alpha, okay, is 31 degrees. Find the torque of this force about the pivot point P. Now take counterclockwise out of paper as positive and clockwise paper or clockwise torque, well, which means into the paper as negative. Now here, we're looking for the following. So if you look at this bar now, we're applying this force, And this force is making an angle alpha relative to the vertical. Okay, something we haven't seen in the slides in the lecture. So here, when alpha, so here, when the angle alpha is with the vertical instead of the horizontal, you need to keep in mind the following. What causes the torque? What causes the torque is always the perpendicular component of force. What causes the torque is the perpendicular component of force, which means this one. The horizontal component, when you project it like this, okay, this horizontal component of force is pointing towards the fulcrum, towards the axis of rotation, okay, or towards the pivot point. Now, here, if you look at this F perpendicular, the perpendicular component of force, if you look at it relative to the angle alpha, what does it represent? So this perpendicular component, what does it represent? So you can clearly see, okay, that this F perpendicular relative to alpha represents the adjacent, okay? So this is the adjacent in this case. So F perpendicular is not the sine anymore. So usually we had, you know, the perpendicular component to be the sine because we were taking the angle, let's call it theta, we were taking the angle theta relative to the horizontal. But now we're giving you an angle relative to the vertical, which means what is going to change in this case? So F perpendicular is becoming now the adjacent to this angle alpha because it's relative to the vertical. Now it's become the adjacent. That means F perpendicular will be magnitude of force times, not sine this time. Now we are used to sine, but it will be cosine theta, which is quite unusual because we are used to sines in the formula for torque. Now, if you remember, we define torque as distance r, okay, between the fulcrum or the axis of rotation to the force, and then multiplied by f sine theta, or for short, f perpendicular. But f perpendicular now is different. F perpendicular is different. So it's not the f sine theta. It's now going to become, instead it will be, now you can use R or you can use L, the length of this bar. Okay, so you can use whatever you want. So here you can call this length of the bar, like we did somewhere here. So here, that would be R, or length, multiplied by force, magnitude of force, multiplied by cosine theta. Okay? Now, this is then the difference. Okay, this is the difference between what we saw in the lecture and what we see here. Okay, when the angle when the angle is provided relative to the vertical, we end up with a cosine, okay, instead of a sine. So something to pay attention for. Now, is the torque going to be positive or negative? Okay, is the torque going to be positive or negative? Now, this force will cause the bar to rotate in this direction, which means this is counterclockwise. So CCW. Now, CCW means the torque, okay? The torque in this case for CCW rotation, the torque will be, or should I say, not equal, but greater than 0. So it will be a positive torque in this case. So the rest is easy. Just plug in the numbers. You end up with this amount of torque being applied. Right. Now, next question. The notes, 1 second. So next question is related to torque. Now we have a massless bar is pivoted at point B and is held horizontally with two forces F1 and F2 applied as shown in the figure. Now if F1 is 210 newtons and F2 is 80 newtons, and then beta is 30 degrees, we're asking you to find alpha. Okay, we're asking you to find the angle alpha. Okay, so here, if we consider the system to be in equilibrium, okay, if we consider the system to be in equilibrium, and here we're considering the pivot point P. So pivoted at point P. Here is point P. Where is it? Here. Okay. So if considering the pivot point to be here, so we're having the following: the net torque relative to the pivot point, net torque relative to the pivot point, will be then torque, the torque due to force 1, okay, then torque due to force 2. Now we're using a plus everywhere, and then I'll be looking at the direction of the torque. Is it clockwise or counterclockwise? Okay. What else do we have? So 1 second. Yes, so we were saying then the net torque equal to 0, and the only forces we have here are force 1 acting at an angle alpha with the vertical. Now remember, when we have the force acting or given at a certain angle relative to the vertical, the torque, okay, the torque would be provided with a cosine, okay, because when you project the perpendicular component of force, okay, this perpendicular component F1 perpendicular will correspond to the adjacent to the angle. So this is the adjacent. That means this is the cosine. This is the cosine, okay, for F1. Now for F2, you can consider this to be the perpendicular component. So this is F2 perpendicular, and this will be the sine. Okay, of course you can slide it here, but this is definitely the sine because this is angle beta. All right, and it corresponds to the opposite side. Okay, so that means here we're dealing with the sine. For force 1, we're dealing with the cosine. We're putting some additional forces, the reactions that are acting directly on the fulcrum, okay, or the pivot point. But because they're acting directly on the, like here, the reactions, we have Rx and Ry. Now, because we have the reactions acting directly on the fulcrum, now those reactions will have 0 torque. Okay, so we're putting them just to, for the sake of enlisting or enumerating all the torques acting on the system, but in the end, they are 0, they are equal to 0. So what matters are the torques due to the two forces. Now, which torque is positive, which torque is negative? Now, you will see that for force 2, okay, force 2, the rotation will tend to be, so this direction, I'm sure you will all agree, it's counterclockwise. So here, torque due to counterclockwise or due to F2, torque due to F2 is positive. This is positive torque. Now, how about F1? F1 will want to rotate clockwise, in a clockwise direction. So here, torque in the clockwise direction will be negative. Now, in this case, so I will have a negative sign. This should be a negative sign at the beginning, not a positive. So that will be minus, okay, the mass. Oh, sorry, we're talking about distance, not the mass. So minus the distance, and the distance is provided as 10 centimeters. The distance is provided as 10 centimeters here. And in meters, it should be then 0.1 meters. Then multiply by force 1, okay? So provided as 210 times cosine alpha. It's not the sine. We're dealing with the cosine like we explained in the previous question. Okay, so this will be the cosine. Then plus 0.4, okay, 0.4 times f2 sine beta. Now it's the sine. That's the, the usual formula we have for torque. Distance r times force times sine, the angle. And now it's at a distance. Okay, force number 2 is at a distance of 40 centimeters. 40 centimeters from the pivot point. Now we simplify all this. So we simplify all this. And we end up with 0.1 f1 cosine alpha, 0.4 f2 sine beta. And in the end, we substitute with the numbers for the force, for the angles. Now keep in mind what I'm looking for here is the angle alpha. Now, of course, you can take, or you can isolate cosine alpha. You can isolate cosine alpha, and you take everybody else, take it downstairs on the other side. So when you do that, cosine alpha, you'll end up with 0.7619. Okay. Now this cosine alpha equal to this value corresponds to alpha equal to 40.4 minutes. So this corresponds to an angle alpha of 40.4 minutes. Okay. So here in this case, then this will be the angle will be extracted using the inverse cosine. Just on your calculators, plug this value in and use inverse cosine to give you the value for the angle. Now, question 19, which expression describes rotational equilibrium? Now, rotational, like we saw many times, okay, like we applied in a number of questions or problems in this midterm and the previous one. So equilibrium or rotational equilibrium will be reached if we have net torque equal to 0. Okay, so if that's the case, then you have the system in rotational equilibrium. Now let's go next. We have the following. A man holds an object of mass 20 or 2 kilograms, sorry, on the palm of the hand with the arm stretched, okay, as shown in the figure. Now use torque equilibrium equation about the fulcrum to determine the magnitude of the force F that is exerted by the biceps muscle. Now when A equals 0.35 meters, B equals 0.05, and the angle theta is equal to 80 degrees Celsius. Neglect the weight of the lower arm. Now here, so in this case, we're looking at the system in equilibrium. So net torque equal to 0. Now what are the torques acting on this system? So you have the torque coming from the weight. Okay, so this torque will be wanting to cause the arm to rotate counterclockwise, okay? While the torque coming from the force, F, in the muscle, okay, in the forearm. Now here the torque will be so if we can look closer into here, you see that the force is acting at an angle theta, and you see the angle theta now is provided with the vertical, not the horizontal. Okay. Now here, because it's the vertical, okay, the angle is with the vertical, I want you to pay attention. The y component of force, so Fy, the y component of force, Fy, see how we calculate it. So Fy will be equal to what? Will be equal to the force times cosine theta. Okay. Now the torque then due to the force will be, now considering that this force here, remember the fulcrum is here, so this force will want to cause a rotation that is clockwise. Okay, this is clockwise. That means I have a negative torque of negative, the distance, I don't know, we can call it R. So we did this here, we call it R1, maybe this one, I'm referring to this. So the distance was negative R1. Write this, so negative R1. Okay. Multiplied by magnitude of force, multiplied by cosine theta. Okay. Now, for the gravitational force, okay, so torque for Fg, all right. So here, instead of R1, because it's given as B, we can just call it B instead. So let me rubber this and call it B just for consistency with the figure. So negative B F cosine, okay, theta. Torque Fg will be a positive torque and will be the distance from the fulcrum to where the force is applied. And you notice it's distance B plus distance A. So that would be A plus B, and then multiplied by Fg, and then multiplied by, of course, in this case, because it's at 90 degrees, acting at 90 degrees, so you will have sine, there will be a sine 90 degrees. This is 90 degrees, and sine 90 degrees is 1, so I'll just put it as 1, okay? Now, let's summarize everything we said so far. The system is in equilibrium, which means torque due to gravitational force plus torque due to the force in the muscle will be equal to 0. Now, you recognize the expression we established together. So this is A plus B times Fg minus B F cosine theta. Okay, so the distance B times F times cosine, with a negative sign because it's clockwise. Okay, it's causing clockwise rotation. Now, the unknown in this case, okay, is the force, the magnitude of force. So plug in all the other numbers, solve for the magnitude of this force, and you get a value of